Okay, so this is going to be a really quick crash course in simple harmonic motion. So imagine you have a spring, and spring is completely happy. When the spring is completely happy, and the spring always wants to get to a complete, where it is completely happy, we're going to call that the equilibrium point, x equals 0. So if I have this happy spring at its equilibrium point, x equals 0, I can stretch it to the right, shown here, and then I let go. And when I let go of this spring that I pull to the right, it moves in this direction here. And it's trying to get back to that equilibrium point where it's happy. So it starts moving to the left, boom, right here. But it overshoots it. It overshoots it, and it comes all the way to this point. And now at this end, it says, okay, now I'm going to go back the other way. I'm going to try to get back to the equilibrium point. I'm going to get right here to the equilibrium point, and it overshoots it again. And this is really a summary of everything that's happening. So the spring started here, I pulled it to the right, and I let it go. And as it tries to get back to the equilibrium point, it overshoots it, goes to here, and then it overshoots it, and it just forever and ever and ever is just going to continue back and forth. From x equals 0, the equilibrium point, to the amplitude, to the negative amplitude. It just forever and ever and ever and ever and ever and ever and ever does that. This is simple harmonic motion. This is periodic motion. And we don't really see this in real life because realistically, if I pull this to the right, it loses energy as it starts, oscillating back and forth. It's just frictional energy. It loses energy into this to the environment, is heat. So if you dropped a ball on the ground, it's not going to keep bouncing up to the same height because every time it hits the ground, it loses energy. It's the same thing here. So I just really want y'all to get used to the idea of, understanding any concept of simple harmonic motion with this simple diagram back and forth. And note that a period is the amount of time it takes to go from here to here and back. A lot of people are completely wrong and they think that this is a period, and it's from here and back. So if I start in the middle and I go here and then I go here, that's not a period. Because I have to go here to here to here to here to here. You have to have the same position that's in the middle. And so let's say I'm starting out at the right. So I go to the right, and then I go to the left, and then I go to the left. You need the same position and the same velocity. So here, here, not a period because I'm going at a different velocity. Here, now I'm going to the right. Here, that's a whole period. If I move over here, we have a guy bungee jumping. Guy jumps off of here, and he is moving downwards. And he goes to a maximum distance down, and then he's going to start moving up. And then he overshoots this point here that maybe we call the equilibrium point. And x might not always be 0 at the vertical equilibrium point. We'll talk about that later. And he gets up to this point here. So he gets up to the top, and then he goes back down. And again, we have this equilibrium. So from here to here to here to here to here, that is a period. Or from here to here, that's a whole period. Amplitude, negative amplitude. Often though, they don't call it the negative amplitude, they just call it the amplitude. Similarly, we could show it with a sinusoidal graph. In the middle, you have the equilibrium. To the maximum height, you have the amplitude. Back down to the equilibrium, negative amplitude, back to equilibrium. So here, I can think of this as going up, then going down. So this is not a period, because this is a velocity going up, and that has a velocity going down. And then, boom. That's from here to here is our whole period. It's a whole wavelength. This is 1/4, this is 1/2, this is 3/4. That is a full period. Okay, so let's say that, same scenario. We have pulled our spring was happy. It was at the center, at the equilibrium position. We pulled it all the way to the right. We let it go, and it starts moving like this forever and ever and ever and ever. So if we look at what's happening right at the very beginning, I'm holding it. I'm holding the block shown right here. And its velocity is 0 because I'm holding it. And as soon as I let go, it still has no velocity because we're talking about time t equals 0.00001. So no velocity yet. In the same way that as soon as I drop this, it doesn't have velocity at 0.0001. It has an acceleration and it picks up velocity as it falls. So no velocity, and it has the maximum acceleration. Why does it have the maximum acceleration? Because the potential energy here is equal to 1/2 kx squared, because we're dealing with the spring, and F equals kx. So the force of the spring, when k is at the amplitude, the biggest value, means that we have the biggest acceleration to the right, or to the left. So the acceleration is going to the left, and so it starts picking up speed, 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 picking up speed. It's now at a maximum velocity. But now its acceleration is 0. So yes, it's moving to the left, but the acceleration is 0. And in fact, as soon as I get into this territory, now acceleration is sort of like a negative value. The acceleration, negative meaning that the acceleration is trying to point in the other direction. So it's at a maximum velocity, but now it's slowing down, slowing down, slowing down, slowing down, slowing down, stops. Now the acceleration is at maximum in this direction. Picks up speed, picks up speed, picks up speed, picks up speed. Maximum velocity. Now the acceleration is in the other direction. Slows down, slows down, slows down, slows down, slows down. It's always trying to get here, but it keeps, like a tragic love story. It keeps overshooting it. Like political discourse, right? One side will be really extreme, and so the other side will be just as extreme, but in the other direction. And so you'll never get at the truth. The truth might be right here in the center, but you just have these two extremes that are sort of working off of each other's energy. And the kinetic energy plus the potential energy is always equal to the total energy in these systems. And they're generally conserving energy. So the potential plus kinetic energy here is the potential plus kinetic energy here. It's always equal to the total amount of energy. It's equal to any other total amount of energy here. Well, the total amount of energy in the center, when you have a maximum velocity, is just kinetic energy. It's the maximum kinetic energy. So you can get away with saying the kinetic energy plus potential energy is just the maximum kinetic energy, which is 1/2 mv max squared. More commonly, you can also get away with saying the kinetic energy plus the potential energy is equal to 1/2 k x max squared. This is the maximum x, and that is technically the negative maximum x, but if you square it, it doesn't matter if it's negative. And we call the maximum x value the amplitude, A. So really, kinetic energy plus potential energy is equal to 1/2 ka squared, and that is often what you see. Kinetic energy plus potential energy is equal to 1/2 ka squared. So if you see a problem where they say the potential energy is half of the total amount of energy, you know what you write that as? You say, okay, that means kinetic energy. If potential energy is the half of the maximum energy, then that means it's 1/2 of 1/2 ka squared. Because 1/2 ka squared always represents the maximum energy. Again, so does 1/2 mv max squared, but you just very rarely see that written out. So 1/2 times the total energy 1/2 ka squared is equal to 1/2 ka squared, which is the maximum energy. If my block starts here, and let's say it's moving to the left at this point. So this is moving to the left here, and then it starts moving to the right, and then it starts moving to the left, and boom, that is one whole period. Let's say that that takes 10 seconds. So it takes 10 seconds to complete one cycle. The period is equal to 1 over the frequency. So if the period is 10 seconds, that means the frequency is 0.1 seconds. That means every 1 second, we complete 1/10 of a total cycle. That's what frequency means. It is how many cycles you are completing every second. We could say a very similar thing about how long it takes to go around the circle. Let's say that this circle, it takes I don't know, about 10. Let's say that's 10 seconds. So it takes 10 seconds to do one cycle. But it's a circle. So instead of calling it a cycle, the amount of time to go all the way around, I could just call that one revolution. That's cool. So a really similar thing. I could say that this frequency is 0.1 revolutions every second. Again, it's just the inverse. Now 0.1 revolutions every second. Remember, for circle, we have a couple different ways we can describe theta. 360 degrees is one revolution. So instead of saying this is 0.1 revolutions every single second, I could technically, if I wanted to get to degrees, 0.1 revolutions over a second. So there are 360 degrees in 1 revolution. Back to general chemistry conversion factors. Revolution cancels with revolution, and I get that this is 36 degrees every second. This is just another way of writing the frequency. Every single second I am going 0.3 or 36 degrees, you know? That's the same thing as saying I am doing 0.1 revolutions every second. Why would you want to say that? I don't know. Somebody just, you know, some mathematician thought that was an interesting way of phrasing it. Well, there's an even more interesting way of phrasing it that they really, really, really want you to know. So instead of saying 36 degrees per second, I could also use the idea of a radian. Don't forget, a radian is just 57.3 degrees, essentially, approximately 57.3 degrees. So this is 1 radian, it's 57.3 degrees. And you can fit, you know, 57.3, 57.3, 57.3, all the way around. You can fit 2 pi radians, in other words, 2 pi, which is approximately 6.28, times 57.3 is about equal to 360. So I can say that 0.1 revolutions per second times 2 pi radians over 360 degrees, or in this case, over 1 revolution, will cancel, and will give me, remember, 2 pi is approximately 6.28, so I can just call this 0.628. 0.628 radians per second. That is just an alternative way of describing the frequency. So instead of saying this is going 0.1 revolutions per second, you know, I guess that's like 0.1 revolutions every single second. I could say it's going 36 degrees every single second, or I could alternatively say it's going 0.628 radians per second. That's all they're saying with the radians per second thing. And this is omega. That's omega. Omega is describing the angular velocity. How quickly are we going around the circle, essentially? So we're relating like a torque angular, you know, motion variable into our harmonic motion thing. Again, it's weird, and you just kind of have to roll with it. They just, you know, it seems stupid. I'm sure there's a better reason for it than I could explain in this really, really quick, rushed video. But omega, the same way that we can describe it as a frequency for going around a circle, I'm going to describe it here, right? If this is f equals 0.1 cycles or revolutions per second, I could equally describe this as omega. Omega is 0.628 radians per second. It's just a conversion factor. You want to say pounds or do you want to say kilograms? Do you want to say cycles per second or do you want to say radians per second? Yes, we're not actually going in a circle, but the idea still somewhat transmits. It's just a weird way of describing how quickly we're completing an entire cycle, an entire period. Yeah, so omega is really, 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 really important for solving pretty much all of these problems. I think omega lies at the center because t is equal to 1 over f. And f, or 2 pi f, is equal to omega. And omega is equal to the square root of k over m. So if I tie it all together, t is equal to 1 over f. So therefore t is equal to 1 over f, which is equal to 2 pi over omega, which is equal to the square root of m over k times 1 over 2 pi. Do I recommend writing it like this? Not really. Sometimes the book does. That's okay. If you want to tie all of these formulas together, that's your call. I wouldn't recommend it. The idea though is that omega sort of lies at the heart of everything. Omega sort of relates to the values of m and k, and it relates to t. So you have to use omega in a lot of these problems. And notice that the only thing that really affects the period is m and k. M and k will decide what omega is, and omega decides what f is, and f decides what t is. So only by changing the mass of the k will you essentially change what your total period is. We have a really similar thing here with pendulums. Let's say I had a pendulum right at its equilibrium position. Equilibrium is where they want to lie at rest. So it's happy just kind of hanging there. And then I pull it up, and I let it just start moving like that forever and ever. So I pull it out, and I let go, and it just goes whee, just forever and ever and ever, because we're not losing any energy in these imaginary problems. Just keeps on going like that. They tend to consider counterclockwise. This would be clockwise. So this will be negative a, and this would be positive a. Whoopsies. So if this is the equilibrium, this is clockwise of the equilibrium, so this is x equals negative a. As I let it go, it is now moving in the counterclockwise, in other words, positive direction to x equals a, and then it's going to fall backwards. And it's going to go like that, and then like that, and then it's going to forever and ever go back and forth, equilibrium, amplitude, theta, and importantly here, omega is no longer equal to the square root of k over m. It's now equal to the square root of g over L. So the common question is, if you make this go from 1 kilogram to 10 kilograms, will the period change? Well, does changing the mass affect omega? No. And omega is proportional to F, which is proportional to 1 over T. So no, changing this doesn't change omega, which won't change T. So no, the only way you'll change T for the most part is if you change G or L. So this is modeled after, I think it's chapter 14, question 8 or 9, or maybe 10. It is the vertical equilibrium question where you had to rank them for mastering physics. These are harder types of questions, so I'm going to just kind of run through the basic scenario of how you would solve this. I think they gave you a bunch of different original length original, and then they gave you different length final, L, like final compressed, and they gave you different K values, K equals something, and they wanted you to rank, several different of these scenarios based off of the period. How long does it take one of these to go all the way down and then back up versus another with different variables? And it was pretty tricky. A lot of people came to me with questions on this. So here's the idea. We have a spring. It is, I just made up, let's say the original length is 10. It's totally happy. It's just going to sit there forever if we don't touch it. Happy things that are, that have no net forces on them, and actually I guess not even no net forces, that just don't want to move and happen to have no net forces, is our equilibrium point. So we call this x equals 0. So we have this x equals 0, and then boom, I put a big mass on it. And the whole thing's going to start coming down. Notice right initially, I'm saying just as I put the mass on it, x is still 0, it's still at its equilibrium point, it's still a total length of 10. So there is no force spring, because force spring is equal to kx, and x is 0. But there is a force gravity, so it is going to start moving downwards. And here's just a picture of it at 7.5, so it's compressed 2.5 centimeters. So actually we can write that in. X in this case is 2.5. X was 0, it goes from 10 to 7.5, so x is 2.5. Here L is 5, so x is 5. It was 10, it is now 5, so it has compressed from its equilibrium point a value of 5. Notice here that the spring force must be a lot bigger than the gravitational force, because this is as far down as the whole thing goes. So at this, presumably, it's going to go upwards. So the spring force would have to be bigger than the gravitational force. So it seems like this thing is oscillating somewhat like this. This is x equals 0. This is x equals 2.5, and this is x equals 5. So gravity brings it down, and then the spring force brings it up, and then gravity brings it down, and the spring force brings it up. These vertical problems are harder and a little different because in the middle, we're so used to staying in the middle. The equilibrium point, x is 2.5. We're used to saying x is 0 in the middle, but it's different here because x is 0 at the top. In the middle, we still have an x value. But I still consider this somewhat of a pseudo equilibrium point. Because this is still where we have our maximum velocity, and it's still where we have our acceleration equal to 0. So it's basically equilibrium, except x is not 0. That's the major difference. And so that's going to lie right smack dab in the middle. So that's why I even drew this 7.5. It is because this is where our acceleration is 0. And if the acceleration is 0, what are the two forces on this? Force gravity going down, force spring going up. That means that the force of the spring at this pseudo equilibrium point is equal to the force of gravity. So force spring, kx, is equal to force gravity, mg. Okay, big one. big whoop. What are we even trying to figure out? We're trying to figure out the period. How long does it take for this thing to, I put on the mass and it goes, how long does that take? Well, the period is equal to 1 over f, which is equal to 2 pi over omega, which is equal to, omega is equal to the square root of k over m, so if omega is the denominator, it's equal to m over k, and I want to get rid of this thing there, something like that. But we really aren't even interested in the 2 pi. It's for the most part irrelevant, because we're just comparing one to the other. And if they all have 2 pi, then I can ignore 2 pi. Okay, so it's equal to the square root of m over k. So that's really all. I'm more interested in proportionalities. If I have f be twice as big, t is twice as small. If omega is twice as big, t is twice as small. Proportional to the square root of m over k. So if my mass is twice as big, my period is twice as big. If my k is twice as big, my t is, well, I guess it's not necessarily twice because of the square root. But if my m is bigger, my t is bigger. If my k is smaller, my t is smaller. Got it? They didn't give you the mass though. Oh, that was the kicker, because they gave you k, and if they had given you mass, this problem would have been easy, but they didn't. So we have to be clever. How can we get mass? What can we plug in for mass? This guy right here, kx equals mg. Let's take a better look at this. Kx equals mg. I really hope the camera can see this. If you can't, this says kx equals mg, and then m is equal to kx over g. Okay, I'm going to plug that in over here. Boom. M equals kx over g. And what does this give me? This gives me t is proportional to the square root of kx over k times g. And the k's cancel, and I get t is proportional to the square root of x over g. Now this x in particular, mind you, is, our unstretched, our original length is 10, our final length is 5. So the total difference is 5 in this particular example. So that means our equilibrium, our pseudo-equilibrium x is 2.5. So you would use 2.5 for this value. But that also doesn't really matter because, if we're looking at the difference between a length of 10 and 20, 20 minus 10 will be equal to 10. Like if you plugged in 10 for one of these, and then for another one, you did 10 minus 5 equals 5, we would say then that the one with 10 is going to be a bigger period than the one with 5. And that would be the same thing if you did, the 10 minus 5, technically this should be 2.5. But it's essentially the difference between 2.5 and 5, plugged in up here, is the same as the difference between 10 and 5. Not sure how articulate that was, but long story short, if you figure out what the x value is at this, which is 10 minus 5 is 5, half of that is 2.5, and that's what our x is right at the pseudo-equilibrium point. And that's what we're plugging in here. You'll figure out your period and you can rank them pretty easily. Boom, okay, that was the thing. I went really quick. I'm kind of rushed for time. I gotta be somewhere. Thanks, hope it was helpful.